FinFET. So last time we already discussed some of the basic aspect of FinFET, right? So we will try to look at it from different directions. Some of the knowledge we have already learned it, but we try to look at different directions, and then eventually we have a better appreciation of what FinFET is about. So if you remember, the FinFET has the channel building on top of the wafer. Here I have box. Probably I did not really spell this out before. Do you know what is box, by the way? Very good. Buried oxide. So if you have not encountered box, but you should have encountered oxide, right? So this is just like a fin on top of oxide. What type of FinFET is this? We have two types. We discussed two types, right? Do you remember what the two types of FinFET? SOI and bulk, right? Bulk. But this is SOI. So that's what we covered in the last class, right? So it is just like SOI, but however, it operates as a FinFET because it's three-dimensional, right? We have this fin going up. Now, then what does it look like? If you remember, the current should go into the screen. Do you remember what we did before? For the cartoon we had earlier, this is the fin, right? And then you have a gate wrapping around this fin, right? And where are the source and drain? This is the source, this is the drain, right? So what we are looking here is a cross-section of FinFET. Cross-section, meaning that we are looking into this direction from source to drain. Okay, so it's looking into it. Now here we have a SEM, scanning electron microscope, showing a FinFET. It has many fins. Do you see this? And where are the source? This is a group of source. This is a group of drain. And actually it's labeled here already. What we are seeing here, if I cut this in this direction, cut it. I call this A dash. That is what we have here, A dash. Make sense? Okay. So if we don't have multiple fin, we only have one, then this is like this, right? Here the gate is not shown, by the way. Okay, I think they did the SEM before the gate patterning. So you don't see the gate, so you don't have this purple part wrapping around this fin. This is the fin. Right? Let me make it very clear. This one is one of the fins. Okay? So in a FinFET, of course, at the middle, you have the silicon or silicon germanium. This is channel where the electron and hole transport. Then you have this layer. Do you know what is this layer? What does it supposed to be from a MOSFET concept, from a transistor concept? What should be the insulator, right? Yes. Yeah. You are one step further. You say usually it's high K, but let's just assume it's insulator. Then on top of it, this will be either polysilicon or the metal. Any questions? Let's ask now, right? It's easier to understand if we discuss now. Yeah. It should be pretty slim for a few reasons. Let me finish writing this. So he's asking about what if we have the gauge on the as in the SEM picture. First of all, the gate length, how thick you are, how wide you are in this direction, is the gate length. So this needs to be small in FinFET. That's why we use FinFET, because it can go to 20 nanometer or below, right? So here the source string probably is pretty long. That's the first thing, right? But however, this is an old technology. This one came from a book like in early 2000 or late 2000. Okay, so this is just a demonstration. Because I think your second question is, if this is very thin, then you have such a wide SS region. That's not a good thing. So you're right, yeah. So this is it's not the state of the art. So just treat it as a cartoon for now. Okay, there's one thing. Another is that the gate will not be very thick as this one, as a source string. So yeah, so let's treat this as a cartoon. So yeah, okay. Now, more than later, we'll see that. Okay. So are you okay with this cross-section and the 3D picture? Now, then how about the layout? You are familiar with this layout, right? This is the bulk. You just done in assignment 1, right? So you have a diffusion or active region, which is the greater area. You put a poly on top of it, then this becomes source, this becomes gate, and become drain, and this is the gate. Is that okay? Remember this? Now, then how about FinFET? One possibility is that, now, of course, this is planar, right? But in terms of layouts, they can be similar, but I just make them into slotted structure. So this one is going to be a fin. When I put this gate, for this one, it is just a flat gate on top of the silicon. But this one is going to go through this topology like this one here, right? So let me be clear. Let's look at this. If I already say something, this is A, this is A dash, and this is what you have when you cut from top to bottom. So you have this type of topology, right? If you look at this one, how about for this one? Maybe use another color, so when you study, you know that I'm referring to different things. This one. I call it B, B dash. When you cut it, what do you see? Straight. Yes, you actually see a straight poly gate or metal gate. And that's it, that's it. No source string because I'm cutting in this direction, right? And then under it will be, let's say maybe P-type, the body, that's it. Do you see this? Cutting this, I get this. Cutting this is not flat, I have this. Because in this planar case, the electron or the hole will go into this direction, go into the plane on the surface. Here, it go into the fin. Into the screen. Any questions? It's not easy to visualize, so ask, yeah. No, A is the A dash is a cross section that I drawn, and this is a mass of the FinFET. You're looking from top of the wafer, right? So when you cut it, then you will see this cross section. You mean this one? Oh, sorry. Yes, this bulk. This is FinFET. Yeah. This is just a regular bulk device that you have drawn. Right? To be more specific, maybe some of you feel uncomfortable with this. Actually, outside the gate, you have something called STI, which is an isolation. It's outside. You just isolate this device. Okay. So this is not a source string direction. Source and drain are into the plane. Okay? Okay, good. So that is the first exercise. We will understand more when we keep playing with this. So I repeat this figure. And then how about let's try to estimate the current. It is a toy model, completely inaccurate, but it's good for educational purpose. What is the current? How do we find the current? Because this is source, this is drain. We are asking what is the current going from source to drain or drain to source? That is the question we want to ask, right? In each of this fin, right? In each fin, if you look at the cross section that I drawn to you earlier, silicon, oxide, and then gate, right? This is each fin. Are you okay with this? It's like flowing the current is going into the plane, right? So what I'm saying is like, how much going to here is only like through this channel, right? And that is how much going in. Now the point is, this thing is very narrow, so you can consider it has three interfaces. Here we call it H, and here we call it W. Okay, so H is the height of the fin, which you cannot see from here. And actually, instead of calling it W, I will follow the figure. I call it WSI, this one. Right, so do you see that? The width is the WSI, each of them. Yeah. This is the fin. The gray one is the fin. Yeah, the white one is the gap. Very good. Good point, right? So this is fin. Okay. So what is the total current? Just a toy model, right? Of course, the total current is going to be I just say proportional. Proportional to the N. N is the number of fins, right? If I have N, then I have N times of the current. And definitely, it depends on the height. But I have two channels. Remember, this is a tri-gate. We mentioned this last time. It is a tri-gate. These two are double gates, right? I have this height conducting the current. At the same time, I also have the width conducting the current, because your width can be very wide if you don't do it well, right? Or you deliberately do that. So that is this one. And then, of course, it's proportional to the mobility. That is the total current. Right? Why we write that? We don't get anything, but I hope that you understand the basic thing. Yeah.
So,
no, for as a circuit designer, you can design WSI, but you cannot control H. H is the foundry defining it. Oh, you can make it wide, but it becomes lousy. The point is the FinFET actually rely on the conduction on the lateral channel, on this vertical channel. It's not the surface. If it is surface, then it becomes an SOI. Think about WSI is very wide. Then it's no longer a fin, right? Or SOI, right? Yeah. So yes, so in most of the technology, right, people try not to use the WSI, right? Because we want to make it very narrow to have a good gate control. If you have a wide WSI, then you are going to screw up the short channel effect.
so essentially,
Yeah, and then now maybe I say something not that accurate. I just say that the circuit designer can control WSI, but I think you don't have much control because this one will actually make it lousier. So I never tape out a FinFET chip, so I don't know. But definitely you cannot control to any extent you want. It might violate the DRC. And now this tells us something. If you want to have certain current, all you can do is just to have a multiple of the fin. You cannot say, I want to have 3.5 fin of current. So your current is digitized. Yeah? So that's why I bring me back. I should not say that you can control WSI. You almost cannot control. Yeah. Yeah, because I have two channels. This is the oxide, right? Exactly, two interfaces. Exactly. And that's why it's a double gate, right? Now, this is one thing, but we can further say that, of course, N is equals to the total width divided by the pitch, right? Number of fin here is the total width. This is the total width divided by the pitch. Pitch is the distance from one fin to another fin. Then you get this one. Another thing is that, if you remember, we already discussed last time, you don't have the same mobility on different surface. Last time, some of you asked further, it's not clear to you why you have different orientation, right? The transport direction of the electron is into the screen. So one same direction, right? Whether you're conducting on this interface or this interface, they have the same direction. So you think that they have the same mobility. That is true for bulk silicon. But now we have interface. You also have surface roughness scattering. And surface roughness scattering depends on the crystal orientation. So this phase and this phase have different orientation. So last time I explained to a student, just like this room, when I want to travel from here to the bed, someone can push me against the window, right? That is the electric field, and I walk to the back of the room, right? I get certain type of surface roughness scattering. Here I have window and this pillar. If I'm on the space, I can also be pushed against the floor or against the ceiling. The environment are completely different. So although I'm traveling in the same direction, but if I'm pushed against the ceiling, I feel different type of roughness compared to against the window. So one will be travel faster, one will be travel slower. And that's why, I don't know if all of you watched the video already, when we talk about the mobility, we'll say what is the transport direction. Maybe this is 100 into the screen, but it can be along a 100 interface or still 100 direction, but along a 110 interface, right? So basically, this is just like 100 means I'm traveling from here to the back of the classroom. I'm same direction, but maybe I'm pressed against the ceiling or I'm pressed against the window. Then you have different mobility. Is that clear? I'm going to remove this because you will get confused when you read the note. Okay, so because of this mu is not that accurate. We actually need to say 2h times the mu. We call it sidewall. This is the so-called FinFET sidewall mobility. Plus the width of the silicon times the top channel mobility, whatever you want to call it. Make sense? Usually, they are not the same.
Direction on the side or elongation along the
Why do we have a different direction?
Yeah.
That depends how you rotate a crystal. Yeah, if you do it just correct, maybe this is 100, this is 010, then the direction will be the same. But think about if this is 111. This cannot be 111 because they are not perpendicular to each other.
I travel into the board like you did there,
Mm-hmm.
and then how it's not exactly the same if I'm closer to the top or I'm closer.
Because of the surface roughness scattering. We're traveling in the same direction. Most are the same, but because I'm pushed against the interface, right? I have surface roughness scattering.
So why is it different than the
Because the crystal is anisotropy, right? Remember? What if I tell you that where the atomic density is different in different direction of the crystal? Do you agree with that?
Yeah.
Yeah. So if they have different density, then think about they have different roughness, different defect, density of states, defect. Once you have different density, when you react with oxygen, they have a different density of defect.
So
Yeah.
far.
No, not far. I'm saying that you are pushed against the wall. For two reasons. One is high electric field, you push against it. Second is the electron is a wave function, is a quantum object. So it's a wave. You do have wave. Even you travel at the middle, you do have some wave penetrate to it. You just go through the quantum mechanical calculation, you will feel the roughness here. Okay, so now we are not talking about one electron traveling at the middle. We're talking about pretty classical, is that most of the electrons are residing at the interface. So you really can distinguish three interface, three streams of electron. Free stream. So I only put a cross here that may be confusing. You think that I'm only talking about it travel in this direction, but actually you have an inversion layer here, inversion layer here, inversion layer here. Just like in extreme case, it's just like you have three transistors stitching together. Now that makes sense, right? Yeah, now I understand. So the confusion was you think that I'm saying the electron is traveling at this point, but actually you have three inversion layer. Yeah.
Well, there's a bit of constructive rapidly.
Yeah, that's nano wire. So we'll discuss that a little bit later. Maybe I don't have the I probably don't have the material. Now this is only 3 gates, right? So nowadays what happened? Maybe next time I will bring you some material. So this is nano wire. You wrap it with oxide, and then they wrap it with metal. Okay, so then, yes, so that is the ideal case of the short channel effect mitigation. Okay, this is nano wire. But it turns out from manufacturability point of view and also device electrical characteristic trade-off point of view, nanowire is not the best. Nano sheet is the best. A sheet, right? Instead, I don't hope my pronunciation is okay. This is sheet. Thank you. So this is the gate. Yeah, so you make it elongated. Okay, and that is nowadays in the, are they in production already? But anyway, they N3 nodes, N2 nodes, they all use nanosheet. TSMC, they are leading. Intel, I think they are following, and Samsung also. Yeah. And yeah, so that's it. But I did not go into detail. Actually, we will stack them. Now the process is very complicated. Maybe, let me see if I can find some example next time show you. Yeah, but this is not a pure device, guys. It's cryogenic. Okay, any questions? Now, if no, then we continue to talk about FinFET. Now, FinFET is